Welcome friends. In this session, the concept of triple integral will be introduced. Some of the properties of triple integrals and the method of evaluating a triple integral in regular three-dimensional domain will be discussed. As an application of triple integral, volumes of some solids will be evaluated. The formula for finding the average value of a function f over a region D will be discussed. Triple integral. Triple integral is a generalization of a double integral. Let V be a given three-dimensional domain in space bounded by a closed surface S. Let f of x, y, z be a continuous function of three independent variables x, y and z defined on V. We divide V into subdomains delta Vi. Let f of Pi be the value of f at an arbitrary point Pi of delta Vi. Then a triple integral of f over the domain V denoted by triple integral over V fp dv is defined as limit delta Vi tending to 0 sigma f of Pi delta Vi is equal to triple integral over V fp dv, which is equal to triple integral over V f of x, y, z dx, dy, dz. Equation number 1. The triple integral is seldom evaluated directly from its definition 1 as a limit of a sum. Remark: if f of x, y, z greater than 0 is the volume density, that is mass by unit volume of distribution of mass over V, then the triple integral 1 gives the mass contained in V, that is mass is equal to triple integral over V f of x, y, z dx, dy, dz. Properties of triple integrals. Triple integrals have the same algebraic properties as double and the single integrals. If f is equal to f of x, y, z and g is equal to g of x, y, z are continuous functions defined over V, then 1. Triple integral over V k into f dv is equal to k into triple integral over V f dv, any number k. 2. Triple integral over V f plus or minus g dv is equal to triple integral over V f dv plus or minus triple integral over V g dv. 3. Triple integral over V f dv greater than or equal to 0 if f greater than or equal to 0 on D. 4. Triple integral over V f dv greater than or equal to triple integral over V g dv if f greater than or equal to g on D. 5. Triple integrals also have an additivity property. If the domain V of a continuous function f is partitioned by smooth surface into a finite number of non-overlapping cells V1, V2, etc. Vn, then triple integral over V f dv is equal to triple integral over V1 f dv plus triple integral over V2 f dv plus etc. plus triple integral over Vn f dv. Evaluation of a triple integral in regular three-dimensional domain. A subset V of a three-dimensional x, y, z space is said to be a regular three-dimensional domain or regular three-dimensional region if 1. Every straight line parallel to z axis and drawn through the interior, that is not lying on the boundary S, point of V cuts the surface S at 2 points. 2. Entire V is projected on the xy plane into a regular two-dimensional region R. Some examples of regular three-dimensional domain are parallelopiped, ellipsoid and tetrahedron. Let the equations of these surfaces bounding a regular three-dimensional domain V below and above B, z is equal to z1 xy and z is equal to z2 xy respectively. Let the projection R of V onto xy plane be bounded by the curves y is equal to y1x and y is equal to y2x and x is equal to a, x is equal to b. Then the threefold integral IV of a continuous function f of xyz over a regular domain V is defined as IV is equal to integral x is equal to a to b, integral y is equal to y1x to y2x, integral z is equal to z1 xy to z2 xy, f of xyz dz dy dx. Here the limits of integration are chosen to cover the domain V by varying z from lower surface z is equal to z1 xy to the upper surface z is equal to z2 xy and covering the projection R by varying y from y is equal to y1x to y is equal to y2x and x from a to b. In the threefold iterated integral, integration is done first with respect to z, that is within the square brackets, with the substitutions of limits for z. The next integration is carried with respect to y, that is within the braces. This results in an integrand which is a function of x along, which is then integrated with respect to x between a and b. Remark: when V is projected onto xz plane or yz plane instead of xy plane, then the order of integration and the limits are to be rewritten appropriately. Example 1. Evaluate integral 0 to 1, integral 0 to 2, integral 0 to 2 x square y z dz dy dx. Solution: integral 0 to 1, integral 0 to 2, integral 0 to 2 x square y z dz dy dx is equal to integral 0 to 1, integral 0 to 2 x square y z square by 2 over the limits 1 to 2 dy dx is equal to integral 0 to 1, integral 0 to 2 3 by 2 x square y dy dx, which is equal to 3 by 2 integral 0 to 1 x square y square by 2 over the limits 0 to 2 dx, which is equal to 3 into integral 0 to 1 x square dx, which is equal to x cube over the limits 0 to 1, which is equal to 1. Example 2. Evaluate integral 1 to 3, integral 1 by x to 1, integral 0 to root xy, xyz dz dy dx. Solution: integral 1 to 3, integral 1 by x to 1, integral 0 to root xy, xyz dz dy dx is equal to integral 1 to 3, integral 1 by x to 1, xyz square by 2 over the limit 0 to root xy dy dx, which is equal to 1 by 2 integral 1 to 3 integral 1 by x to 1 x square y square dy dx, which is equal to 1 by 2 integral 1 to 3 x square y cube by 3 over the limits 1 by x to 1 dx, which is equal to 1 by 6 into integral 1 to 3 x square minus 1 by x dx, that is equal to 1 by 6 times x cube minus log x over the limits 1 to 3, that is equal to 1 by 18 26 minus log 27. Example 3. Evaluate triple integral over V 1 by x plus y plus z plus 1 whole cube dx dy dz, where V is the volume bounded by the planes x is equal to 0, y is equal to 0, z is equal to 0 and x plus y plus z is equal to 1. Solution: referring to figure 1, we have the region V of integration is 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1 minus x, 0 less than or equal to z less than or equal to 1 minus x minus y. Hence, triple integral over V 1 by x plus y plus z plus 1 whole cube dx dy dz is equal to integral 0 to 1, integral 0 to 1 minus x, integral 0 to 1 minus x minus y dx dy dz by x plus y plus z plus 1 whole cube. That is equal to integral 0 to 1, integral 0 to 1 minus x, integral 0 to 1 minus x minus y dz by x plus y plus z plus 1 whole cube dy dx. That is equal to integral 0 to 1, integral 0 to 1 minus x dz by minus 2 into x plus y plus z plus 1 whole square over the limit 0 to 1 minus x minus y dy dx. That is equal to minus 1 by 2 times integral 0 to 1, integral 0 to 1 minus x 1 by 4 minus 1 by x plus y plus 1 whole square dy dx. That is equal to minus 1 by 2 integral 0 to 1 y by 4 plus 1 by x plus y plus 1 over the limit 0 to 1 minus x dx. That is equal to minus 1 by 2 integral 0 to 1 1 minus x by 4 plus 1 by 2 minus 1 by x plus 1 dx. That is equal to minus 1 by 2 times x by 4 minus x square by 8 plus x by 2 minus log x plus 1 over the limit 0 to 1. That is equal to minus 5 by 16 plus log root 2. Application of triple integrals. Volume by triple integral. Volume of a solid contained in the domain V is given by the triple integral. Triple integral over V f of x y z dx dy dz with f of x y z is equal to 1. Definition. The volume of a closed bounded region V in space is V is equal to triple integral over V dV. That is equal to triple integral over V dz dy dx. Equation number 2. Example 4. Find the volume of the region D enclosed by the surfaces z is equal to x square plus 3y square and z is equal to 8 minus x square minus y square. Solution. Using 2, the volume of the region D is V is equal to triple integral over D dz dy dx. To find the limits of integration, for evaluating the integral, we take the following steps. Step 1. The given surfaces z is equal to x square plus 3y square and z is equal to 8 minus x square minus y square intersect on x square plus 3y square is equal to 8 minus x square minus y square, that is on the elliptical cylinder x square plus 2y square is equal to 4. Hence, the boundary of the region R, the projection of D onto the xy plane is an ellipse with the same equation x square plus 2y square is equal to 4. The upper boundary of R is the curve y is equal to square root of 4 minus x square by 2. The lower boundary is the curve y is equal to minus square root of 4 minus x square by 2. A rough sketch is given in figure 2. Step 2. The z limits of integration. The line M passing through a typical point xy in R parallel to the z axis enters D at z is equal to x square plus 3y square and leaves at z is equal to 8 minus x square minus y square. Step 3. The y limits of integration. The line L through xy parallel to the y axis enters R at y is equal to minus square root of 4 minus x square by 2 and leaves at y is equal to square root of 4 minus x square by 2. Step 4. The x limits of integration. Putting y is equal to 0 in x square plus 2y square is equal to 4, we obtain x is equal to minus 2 and x is equal to 2. Hence, as L sweeps across R, the value of x varies from x is equal to minus 2 to x is equal to 2. Hence, the volume of D is V is equal to triple integral over D dz dy dx. That is equal to integral minus 2 to 2, integral minus square root of 4 minus x square by 2 to square root of 4 minus x square by 2, integral x square plus 3 y square to 8 minus x square minus y square dz dy dx, which is equal to integral minus 2 to 2, integral minus square root of 4 minus x square by 2 to square root of 4 minus x square by 2, 8 minus 2 x square minus 4 y square dy dx is equal to integral minus 2 to 2, 8 minus 2 x square into y minus 4 by 3 y cube over the limits y is equal to minus square root of 4 minus x square by 2 to square root of 4 minus x square by 2, which is equal to integral minus 2 to 2 times 8 minus 2 x square into square root of 4 minus x square by 2 minus 8 by 3 4 minus x square by 2 raised to 3 by 2 dx, which is equal to integral minus 2 to 2 8 times 4 minus x square by 2 raised to 3 by 2 minus 8 by 3 times 4 minus x square by 2 raised to 3 by 2 dx, that is equal to 4 root 2 by 3 integral minus 2 to 2 4 minus x square raised to 3 by 2 dx. Now putting x is equal to 2 sin t, the right hand side of the above gives the value 8 pi root 2. Hence, V is equal to 8 pi root 2. Example 5. Using the idea of triple integral, find the volume of the solid enclosed by the sphere x square plus y square plus z square is equal to a square. Solution. Because of symmetry, the required volume is 8 times the volume in the first octant of the solid enclosed by the unit sphere centered at the origin. Hence, if V is the total volume, then V is equal to 8 times triple integral over R dz dy dx, where R is the region of the sphere in the first octant. Now, on the region of integration R, z varies from z is equal to 0 to z is equal to square root of a square minus x square minus y square. Y varies from y is equal to 0 to y is equal to square root of a square minus x square, and x varies from x is equal to 0 to x is equal to a. Hence, V is equal to 8 into triple integral over R dz dy dx is equal to 8 into integral 0 to a integral 0 to square root of a square minus x square integral 0 to square root of a square minus x square minus y square dz dy dx, which is equal to 8 into integral 0 to a integral 0 to square root of a square minus x square is set over the limit 0 to root of a square minus x square minus y square dy dx, that is equal to 8 into integral 0 to a integral 0 to square root of a square minus x square root a square minus x square minus y square dy dx, which is equal to 8 into integral 0 to a square minus x square by 2 sin inverse y by square root of a square minus x square plus y by 2 square root of a square minus x square minus y square over the limit 0 to square root of a square minus x square dx, that is equal to 8 into integral 0 to a square minus x square by 2 sin inverse 1 dx, that is equal to 8 integral 0 to a square minus x square by 2 into pi by 2 dx, that is equal to 2 pi integral 0 to a square minus x square dx, that is equal to 2 pi a square x minus x cube by 3 0 to a dx, that is equal to 4 by 3 pi a cube. Example 6. Set up the limits of integration for evaluating the triple integral of a function f of xyz over the tetrahedron D with vertices 0, 0, 0, 1, 1, 0, 0, 1, 0 and 0, 1, 1. Solution. Step 1. A rough sketch of D along with its shadow R in the xz plane is given in figure 3. The upper, that is right hand bounding surface of D lies in the plane y is equal to 1. The lower, that is left hand bounding surface lies in the plane y is equal to x plus z. The upper boundary of R is the line z is equal to 1 minus x. The lower boundary is the line z is equal to 0. Step 2. The y limits of integration. The line through a typical point xz in R parallel to the y axis enters D at y is equal to x plus z and leaves at y is equal to 1. Step 3. The z limits of integration. The line L through xz parallel to the z axis enters R at z is equal to 0 and leaves at z is equal to 1 minus x. Step 4. The x limits of integration. As L sweeps across R, the value of x varies from x is equal to 0 to x is equal to 1. The integral is integral 0 to 1, integral 0 to 1 minus x, integral x plus z to 1 f of x y z dy dz dx. Order of integration in triple integrals. We know that there are sometimes but not always two different orders in which the single integrations for evaluating a double integral may be worked. For triple integrals, there could be as many as 6 as illustrated in the following example. Example 7. Each of the following integrals gives the volume of the solid shown in figure 4. A. Integral 0 to 2, integral 0 to 1, integral 0 to 1 minus y dz dy dx. B. Integral 0 to 1, integral 0 to 2, integral 0 to 1 minus y dz dx dy. C. Integral 0 to 1, integral 0 to 2, integral 0 to 1 minus z dy dx dz. D. Integral 0 to 2, integral 0 to 1, integral 0 to 1 minus z dy dz dx. E. Integral 0 to 1, integral 0 to 1 minus z, integral 0 to 2 dx dy dz. F. Integral 0 to 1, integral 0 to 1 minus y, integral 0 to 2 dx dz dy. Average value of a function in space. The average value of a function f over a region D in space is defined by the following formula. Average value of f over D is equal to 1 by volume of D triple integral over D f dv. Equation number 3. For example, if f of xyz is equal to square root of x square plus y square plus z square, then the average value of f over D is the average distance of points in D from the origin. If f of xyz is the density of a solid that occupies a region D in space, then the average value of f over D is the average density of the solid in units of mass per unit volume. Example 8. Find the average value of f of xyz is equal to xyz over the cube bounded by the coordinate planes and the planes x is equal to 2, y is equal to 2 and z is equal to 2 in the first octant. Solution. A rough sketch of the given cube is given in figure 5. The region of integration is 0 less than or equal to x less than or equal to 2, 0 less than or equal to y less than or equal to 2, 0 less than or equal to y less than or equal to 2, and the volume of the cube is 2 into 2 into 2 which is equal to 8. Also, the value of the integral of f over the cube is integral 0 to 2, integral 0 to 2, integral 0 to 2 xyz dx dy dz, that is equal to integral 0 to 2, integral 0 to 2 x square by 2 y z over the limit 0 to 2 dy dz. That is equal to integral 0 to 2 2 y z dy dz, which is equal to integral 0 to 2 y square z over the limit 0 to 2 dz. That is equal to integral 0 to 2 4z dz, which is equal to 2z square over the limit 0 to 2, that is equal to 8. We note that in evaluating the integral, we choose the order dx, dy, dz, but any of the other 5 possible orders would have done as well. Using the obtained values, equation 3 gives average value of x, y, z over the cube is equal to 1 by volume triple integral over cube x, y, z dv, that is equal to 1 by 8 times 8, that is equal to 1. Now, let us summarize the session. In this session, the concept of triple integral have been introduced. Some of the properties of triple integrals and the method of evaluating a triple integral in regular 3-dimensional domain have been discussed. Volumes of some solids have been evaluated using triple integrals. The volume for finding the average value of a function f over a region D have been discussed. Before moving to the next session, let us try the questions. 1. Evaluate integral 0 to 3, integral 0 to square root of 9 minus x square, integral 0 to square root of 9 minus x square dz dy dx. 2. Evaluate integral 0 to 1, integral 0 to 1 minus x, integral 0 to x plus y e raised to z dx dy dz. 3. Find the volume of the ellipsoid x square by a square plus y square by b square plus z square by c square is equal to 1. 4. Find the volume of the region bounded by the planes z is equal to x, x plus z is equal to 8, z is equal to y, y is equal to 8 and z is equal to 0. Here are some books for your reference. Gorak Prasad, Integral Calculus, Potishala Private Limited, Allahabad. N. Piskunov, Differential and Integral Calculus, Peace Publishers, Moscow. Shanti Narayan, A Course of Mathematical Analysis, S. Chand and Company, New Delhi. Hope you enjoy the session. See you next time. Till then, take care.